the delta load.
This is delta is not load. It's a
delta load.
This is a y load. It's not delta load.
Is it y? Okay.
Yeah.
Because they can say YD transformer. So like.
Yeah, YD transformer is just a primary side and a secondary side.
The transformer is delta.
Yeah.
Oh.
Yeah, you can see. Can you hear me?
Yeah. Guys.
Okay. So this is a delta because you can see this is the phase A, right? This is the phase A. This, the negative point connected to the positive point of phase B.
Yeah.
A to B, B to C. This is a delta connection.
I see that.
But for the load, it's connected like this. Right?
Yeah.
All of the negative points connected to the ground. The neutral point. Oh, this is so that's why the load is a Y connection. Okay, the first approach is to draw the single phase circuit first. If we want to draw the single phase circuit, you need to convert this one to Y connection. So how to do that? Delta to Y, first you need to convert the voltage. So the voltage will be VAN, VAB, this is the voltage, right? 2,400, and this side is a 240. This is a Y to delta connection. So, but we need a Y to Y. How to do that? VAN divided by VA little a and n. This one, what's the ratio here is 2,400 volts, but the denominator is 240 divided by square root of 3. Here is the square root of 3. Because this ratio, VAB of VAN is the square root of 3. It's a line voltage to the phase voltage is the square root of 3. Right? Okay. So what's the ratio for the YY connection? Should be 2,400 volts. The denominator is a 138.6 volts. When you convert delta to Y, the first you need to convert the voltage. The second one, you need to convert the impedance. Okay, so let's name this one as a Z2. This one is Z1. This part is ZC. Okay? So when we convert this one and this one to Y connection, this equation, Z2Y equals to Z2 divided by 3. ZCY equals to ZC divided by 3. Right? When you convert the delta connection to Y connection, your impedance will be divided by 3. Right? This is two important equations. That one, this one, and this one. This is the two equations that are important. For the load, we don't need to do any conversion, right? Because it's already in Y connection. Okay, so what's the single phase equivalent circuit? Z1 we don't need to do any conversion because it's already in Y. And here is the transformer. This side, the Z2Y. And here is the ZCY. This one is your ZL, the Z load. This one is Z load. Okay, so what's the ratio here? Is a 2,400 of 168.6. Oh, sorry, 138.6 volt. This is your single phase circuit. Then we need to do the per unit analysis. For the primary side, for the first, not first, it's fine. For the primary side, what's the voltage base? So for the primary side, what's the voltage base? It's here.
2400.
Yeah, 2400 volts. So what's the Z base? Z base equals to V1 base square divided by S base. Okay, we know the V1 base, but we don't know S base. S base is provided in the question. The three-phase base is 150 kVA. So for the single phase, this one is 50, right? Because the three phase is 150, so single phase is 50. So it's 2400 squared divided by 50K. So the impedance, the Z base is 115 ohm. Okay, for secondary side, for the secondary side, V1 base, oh sorry, V2 base, right now it's V2 base. So 138.6 volts. It's too fast? Okay. So V2 base is this one. How about Z2 base? The V2 base square divided by S base. So what's the S base for the secondary side? Yeah, it's the same. So this one is still 50 kVA. Okay. So the Z base for the secondary side is 0.384 ohm. Okay, so next thing, we need to draw the per unit single phase circuit. So we need to do is convert all of the impedance to the per unit value. For Z1 per unit is Z1 divided by Z1 base, right? the value here. Your Z1 is 0.115 plus J 11.5. And the Z1 base is a 150. You guys still work on this circuit? Any question? Okay, so the per unit value for the Z1 is 0.001 plus J 0.1 per unit. This is the primary side. So for the secondary side, your Z2Y equals to, Z2Y per unit equals to Z2Y divided by Z2 base. Okay? Because your Z2 is on the secondary side. So when you calculate the per unit value, you need to use Z2 base. So what's the Z2? Z2Y. Z2Y is it's a 0.384 plus J 38.4, meaning this is a milliohm. Milliohm divided by 0.84. So your Z2Y per unit is 0.001 plus J 0.1 per unit. So you find these two are the same, right? The per unit value are the same. They are same because I designed this value, so they are same. Okay, it's not always same. Because this, if you find that they are same, it's easier for you to get the answer. Okay, the same thing. We need to do ZCY per unit. This CY, this is the middle part. Okay, so ZCY divided by Z2 base. This one is very large. It's a 548 plus J 379 per unit. It's very large. How about the Z load per unit? It's ZL divided by Z2 base. It's 1 per unit. Yeah.
For the Z2Y per unit,
Okay.
why is 0.384
Oh, this one?
divided by
Okay,
0.384?
because this answer I already provided here. Yeah, this answer is already provided.
So how is it, but for the Z1 per unit, right, it's 0.115 divided by
Sorry,
0.13.
the 1 per unit.
How are those two the same, right? Because the bottom
Oh,
is-
because the base are different.
Okay.
You can see these two bases are different.
The math, though, I'm asking about, because it's like 1 million, right? 1 So 0.384 divided
Here?
by 0.384.
You mean here?
Yeah.
Yeah, this is a million for both.
So 0.384 divided by 0.384.
Yeah, so this one divided by this one is 0.1.
Oh, those million.
Yeah,
Okay.
million. Let me use another color. So do you guys finish here?
No.
No? Okay, so it doesn't matter. I want to put, right now, we already have the per unit value. So we use per unit value here. Oh, it's, we
You can
cannot
erase
put-
it, it's fine.
Sorry, we cannot put it here. Because if you already pre-unionized all of the impedance, we don't have the voltage ratio here. Okay? So your per unit phase single phase circuit is like this. This one is a Z1 per unit, Z2Y per unit, ZCY per unit, and this is a ZL per unit. Okay? After you pre-unionize the single phase circuit, it looks like this. You don't have the voltage ratio anymore. Okay, so what voltage here? We assume this voltage is 1 per unit. Yeah.
Sorry, I can't see the red.
Oh, you can.
From back here. Yeah.
Okay.
You can just label it in black instead of red.
Okay, okay.
Wait.
This one is Z1 per unit, Z2Y per unit, ZCY per unit, ZL per unit. And this voltage is 1. Yeah.
Why are you doing like why are you setting a voltage base for the primary and another voltage base for the secondary? Shouldn't there be only one base for the whole system so that you can compare the results?
S base is the same, but the voltage base, they have different voltage level, right? This is transformer. This side is
Yeah.
always higher than this side.
Isn't the idea of a base to have a base across the whole system so that you can compare the two sides? Oh, okay.
Yeah, S base is the same.
Looks very different.
The V base is different. So you can say if your V base is different, S base is the same, so your Z base is different. Okay? So the next thing is easy because you need to use this one. You need to use this circuit to do the power calculation. Okay, so let's label this current is I what? I per unit. Okay. So when you try to find the power, find that current first. So your current per unit equals to your voltage divided by your impedance. Z1 per unit plus Z2Y per unit plus Z load per unit. This one is parallel with your ZCY per unit. Right? This is a simple calculation. And here, focus on here. Your this one is C. Your middle part is much larger than another two, right? So when you do the parallel, this one is similar as Z2Y per unit plus ZL per unit. Okay? what's your current? So your current is 0.978. The angle is a negative 11.3 degree per unit. This is your current. Then it's easy to find the S-base. The company's power. So your company's power, your input power is I per unit is a V times I per unit. V per unit times I per unit conjugate. So your voltage per unit is 1 and degree is 0. So your S input company's power is 0.959 plus J 0.92 per unit. Okay, this is your per unit power. So convert it to the real power, the real value power. So what's that? What's this? So this one is your P per unit. This one is your Q per unit. So what's your P per unit? Okay, what's your real value for your input power? So P input equals to P per unit times S base. S base is 50 kVAr. So this is a 50 kVA. So this value is a 47.95 kilowatt. This is a single phase. So for the three phase, P3 equals to P in times 3. Then your value is 143.85 kilowatt. Okay, so the second approach 2.
Combine two circuits, yeah.
Approach 2 is use three-phase circuit. Sorry, use the base value. Use base values of three-phase circuit.
Which base?
Z base equals to V base square divided by S base. This is the second approach. So when I use a three-phase circuit, what's the value for this V base? Right now, this V base will be line-to-line voltage. Line-to-line voltage. you cannot use the phase voltage to do the three-phase circuit per unit calculation. And the same, so what's the power here? It's a three-phase power. How about your Z base? Your Z base should be assumed in Y connection. Okay, this is for the base values of three-phase circuit. The same, we have transformers, so we have two sides. For the primary side, the S base is a 150 kVA. So what's your V base? V1 base? Okay, so yeah, right now for your V1 base, do you guys know what's the value here? Yeah, it's a 9 voltage, so it should be 2400 times square root 3. Right? Because this value is your phase voltage, but you need to convert it to 9 to 9 voltage, so times square root 3. Then you can find your Z1 base. This value is 4,156.9 volts. So your Z base is 4,156.9 square divided by 150K. So your Z base 115 ohm. This Z base, you can find this Z base is the same as previous approach. The same value. I will post the notes so you guys can compare this Z base and the previous approach. But for the secondary side, what's your V base? Your S base is the same, so what's your V base? It's a 240 or 240 times square root 3? Yeah, it's just a 240. Well, yeah, it's delta connection. Yeah. So it's delta connection. This delta connection means this voltage is already 9 to 9 voltage. Okay, you can see this is 240 and then this line to this line, right? It's already 9 to 9 voltage. So your Z base, your Z2 base 0.384. You find this one is the same. This one is the same as the previous approach again. So you can find these two different approach, but you get the same Z base. If you get the same Z base, you will get the same per unit values. Okay. If you get the same per unit values here, so you will find the same power. Same per unit power. Okay. The last approach.
I have a question.
Yeah.
So even though in approach 2, we use the base values of 3 phase, when we take the per unit calculations that we get, we still put them in a single phase circuit?
Okay, so if you calculate, for example, if you calculate the power here, this is the per unit power, right? So your real power, when you use per unit power times S base, you will get 3/5 the total power.
But we still model it with just a.
Yes, they'll
a
model
single
that as
phase
like, yeah,
circuit.
single
Okay.
phase.
Okay.
Okay, the last approach, approach 3. Draw the equivalent circuit refer to primary side. Draw the equivalent circuit refer to the primary side. Use this way, you can remove the voltage ratio. How to do that? First, let's draw the single phase. This is Z1, Z2Y, ZCY, Z load. Okay, this one is a single phase transformer, right? We already draw this circuit in the approach 1, so they are the same. But how do we draw the equivalent circuit refer to the primary side? Refer to the primary side, that means put all of impedance on the primary side. So your circuit is like this. This CY prime, Z2Y prime, ZL prime, and this is Z1. So that means you need to convert all of secondary side impedance to the primary side. How to do that? You need to use the voltage ratio. Let's use this one as an example. Z2Y prime equals to, this side is larger, so this one is 2400 divided by 138.6. This is the voltage ratio. Here is a square times Z2Y. You guys can understand this, right? This is a voltage ratio, is square. Okay. Yeah. So next thing, for this side, you just need to calculate the primary side base value. So for this one, only use
Why is it
primary side base value for primary side. For primary because we already refer everything to the primary side. So for this one, how to do the primary side? So V base, V1 base is 2400. S base is 50K. Okay. then you will find your equivalent per unit equivalent circuit the same as this one. Every per unit value is the same. Yeah.
Why are you always finding the equivalent circuit in the end? The question is, you do the per unit analysis, you should find the variables and that's it, right? It's not the question to find the equivalent
Yeah,
circuit.
you don't need, it's not necessary, but this way is help you to understand why we need to do the per unit calculation. If we use the per unit calculation, you can remove the middle part. You can consider it's a simple circuit like this, no voltage ratios. Yeah.
If for some reason you wanted to refer to the secondary side.
Okay, you can do.
You would just like switch your.
Yeah, if you refer to secondary side, just put this one to the secondary side.
And your ratio there would just be flipped. That's it. And
Yeah.
then you would use the
Base value.
the V2 base of the 240 instead of.
Not 240. It's a 138.
I'm sorry. That's what I meant to say.
Yeah.
Okay.
Yeah, it's correct. Okay, next we still use this example.
Have the primary side be of lower windings all the way. And you just have a smaller over a bigger number MCC multiply. You're still doing the ratio.
Okay, so in your question 4, you still have another small questions to find the maximum value. You need to change the load, then find the maximum value. Right? So this is named impedance match. So how to do that? Right now. Okay, let me cancel this part, remove this part, because this one is much larger than this two. So we can ignore this part, okay? The middle part. So your circuit is like this. What's your Z1 per unit? Z1 per unit is 0.001 plus J 0.1 per unit. And the Z2 is the same, right? Z2 is the same. Well, let me change some values. Let's use point. If I use this value, you can find the homework answer directly. This is a 2. This is a 2. This is a 2. Sorry, 3.3. Okay? And right now, we don't know what's your Z load. We don't know what's that. And actually, this is R. Resistance only. So what is R? Find the P maximum. Okay. First, we need to find the current. Let's do more simplify. Simplify. Okay, for this one, you can find your imaginary part is much larger than your real part, right? It's 100 times larger. So let's cancel this part, ignore this part. So your circuit is more simplified. This is just the inductor, and this is your R. Okay, so this one is a J 0.5 per unit, and this R air, we don't know. We can verify, we can change this value. I, P. Okay, so what's the current? Your current is 1 0 degree divided by G 0.5 plus RL. So do you guys understand why here is a 0.5 per unit, right? Because, right? Because this Z1 plus Z2. So this is 0.5 per unit. And the real part is cancelled, is ignored by us. Okay, so, sorry?
Two prime or no?
Z2 prime?
Yeah.
Oh no, when you use a per unit value, you don't need a prime.
Oh, okay.
Yeah, prime just for the real value.
Okay.
Okay, so what's your input power? What's your power? Your power is I squared times RL. Right? So what's your I squared? I squared is 1 squared RL squared plus 0.5 squared times RL. This is your power. So dot find already give you equation how to find the maximum for this one. So that's right here. Your power equals to 1 RL plus 0.5 square divided by RL. This one. To find the maximum for this equation, you need to find the minima for your denominator. Minimize denominator. So how to minimize that? Your RL should be equal to RL 0.5 square. You guys need to remember this equation. So your RL should be 0.5. Right? You guys understand this? Which step? From this step to this one, or this one to this one?
Yes. Top to the middle.
Okay. So it's A plus B is equal or larger than the square AB. Right? That's this equation. This equation is correct. I think in the dot finds class note she provided this equation. So that means the minimum value for this one plus this one, minimum value is the square root A plus A times B. Right? This is the minimum value.
Or is it?
Okay, so right now this is your A, this is your B. This is A, this is B.
Why isn't it negative on one side?
Sorry, where's negative?
In the middle step?
Okay.
Yeah.
There's no negative.
Yeah, why not? You're not setting it, you're setting it equal to 0, aren't you? Or you're not doing that?
He's not doing that.
Okay, you're not.
No idea. Okay. So, yeah. Let's go to the third topic. Is a short circuit and open circuit. Yeah.
So, for my notes, for Tuesday.
Okay, yeah. Thank you. And that's the trick here. Is that true, right?
That's what I had. I could have wrote this.
Yeah. For this equation, yeah, for this equation, when A equals to B, you will get the minimum value. This is your A, and this is your B. Okay, next is open circuit and short circuit test. So in the Dr. Fan's class notes, she already mentioned how to get open circuit test. So here, let's know how to do the short circuit test. First, here is the R2 prime, JS2 prime, R1, JX1. Okay, so this is the transformer, the single phase transformer. Right now, you have the transformer, but you don't know what's the impedance of the transformer. So how to do that? We need to use the short circuit and open circuit. Okay, so for the short circuit, is shorted the secondary side. Shorted the secondary side. So what's your circuit right now? So if the short circuit, your circuit is like this. Just know this part. Okay. Then let's give it a power, or give it a voltage. Give it a voltage. Give it a voltage here. The V1. So this is voltage, and you have the impedance. You can find your you will have a current. And we already know that the middle part, the core part is much larger than your R2 and the X2. So what does that mean? It means when this middle part parallel with the secondary side part is very similar to the secondary part, right? So your circuit is like this. The middle part can be ignored because it's too large. prime Gx prime. Okay, when you give the voltage, you will get the current. And you will also have the power. Because you have voltage, you can measure the voltage, you can measure the current, you will have power. So what's your power? No. We measured that, we calculated the power. So based on V1, I1, and P1, what we can find? First, we can find the R T equals to P1 divided by I1 squared. So what's RT? RT is R1 plus R1 plus R2 prime. R1 plus R2 prime. Okay. Next, we can know ZT equals to V1, ZT magnitude, only magnitude. V1 divided by I1, voltage divided by current is your impedance magnitude. So what's your ZT? Your ZT is RT squared plus XT squared. Then we know the RT, we know the ZT, so we can find XT. XT equals to square root ZT squared minus RT squared. And XT is X1 plus X2 prime. Okay, so we know the total leakage impedance. Can we separate that? Can we separate that to find the R1 and R2 prime? No, we cannot. So we just stop at this stage. We just find the total impedance, total leakage impedance. Okay. So if you do the open circuit test, it's what? Open circuit test is open this side. If we open this side, it's the same as open this side. Open here. So your current one will from here to this point and go back. So your I2 prime is 0. If it's open circuit, there's no current on this side. So you can see, so your circuit only have this part and the middle part. And we know this part is much larger than this one and this one. So your circuit will be like this. Only middle part. So if you do the open circuit, your circuit is only this part. Okay, how to find the RC and the XN? So use that equation. Yeah.
Why did you not have R1 and JX1? I didn't catch that.
You mean how do we ignore? Why we ignore
Yeah.
this one? So, okay, so this one is only related to the leakage flux. Leakage flux is very small. And this part is related to your air gap. Your air gap inductance is very large. So in your real world, this part is always much larger than this part and this part. We don't need to know what's the exact value, but for example, this one is like 0.1 ohm something, and this one is like 100 ohms, always 100 ohms or larger. Okay. Yeah.
You say it's
I2 prime is 0 when it's open circuit.
Yeah, when it's open circuit, there's no current go this way. Okay. We have one more thing. Is a plot the pH curve based on the single phase transformer.
The last screen you were on.
The
Can you
top
go
one?
back a
Yeah,
slide?
go back a slide, please.
Oh, slides. Okay. But I will post that. And I think in the last Thursday class, Dr. Fan already so give this equation. Oh, it's Tuesday. Yeah, this Tuesday.
Nếu như cái số thời dưới này thì cái gen xong rồi cái sensor nó sẽ cộng cái gen nó sẽ là cái
Okay, the last one. This is question 5 of your homework.
Last one was the question 3, right?
No, question 4.
One you did
Question
before.
right.
Question 4.
The question right before.
Yeah. The question 4.
The
You
question
went over
you
two
just
questions
did.
already.
Yeah, one is question 4.2, another is 4.4. And in the next class, I will give you the hints on the homework. So I really suggest that you can read the homework first. Then you can ask me questions. Otherwise, I just give you the limited hints. If you ask me more questions like how can we get that, I can give you the hints. Okay.
When is that?
Sorry?
Next class.
Next class. Yeah.
Homework's due next Thursday.
It's next Tuesday. Okay, plot the pH curve. So when you plot the pH curve, you can see we can just plot B and H directly, right? But in the real world, it's hard to measure B and H. So we need to use other measurements to replace B and H, like voltage and current. Okay, firstly, you need to know this one. First, let's find out which value we use to replace H. So your MMF equals to. Okay, let's draw the circuit first. The circuit like this. This is your transformer. This is the NP of NS, primary side, secondary side. And here is the VP, and this is IP. Okay, so MMF in your transformer in a magnetic circuit equals to NP times IP plus NS times IS. Your IP and IS is your current. IS is here. And your NP and SP is your tensor ratio. And based on the Faraday's law, your F also, your MMF also equals to H times air. The air is your length of your magnetic circuit. H times air. you can find NPIP plus NSIS. If your IS is very small, we can ignore this part, right? And then let me use another marker, another color. If this one is very small, we can ignore that. Then your H times L equals to NP times IP. Your your L is a length, is a constant value. Your tensor ratio is a constant value. So your H, you can consider is linear with primary side current. So we can use IP to replace H, right? So we need to know how to remove IS, how to make IS as 0. So we need to make this side is open. If this side is open, IS is 0, right? You have two ways to make this one is open. First, just don't connect anything here, make it open. Another thing, add a very large, like 1 mega ohm, very large resistance. Then your current is very small, so you can consider it's open. That's why I provided a 1 mega ohm there. Okay, so we use primary side to replace H. The next, how to replace B. The flux density. We know this equation, the B equals to phi divided by the area, the cross-section area. We know the flux, the phi is lambda divided by tensor ratio. And here is the A. Tensor ratio is a constant, A area is a constant, so we can use lambda to replace B. But it's harder to measure the lambda, the flux linkage. We have another equation. Vs, let's see, Vs. Vs, this is the induced voltage equals to d lambda dt. We cannot use this format. Vst equals to d lambda dt. If we write it in phasor, it's a Vs equals to j omega lambda. So you will find, can we use a Vs to replace lambda? Can we do that? Yeah, but you can see there's a phase shift. There's a J there. So there's a 90-degree shift here. So that means this one is always leading lambda. Vs is always leading lambda. So we need to make them in phase. So reduce the angle for Vs. How to do that? We need to add a capacitor here. A small capacitor, like 1 mu farad. Okay, so the voltage on the capacitor is a Vc. What's your Vc? So Vc is a Vs. We can use the voltage division. Vs, the capacitor, and R plus 1G omega C is a voltage division. we know the R is much larger than this part. It's not default. We designed that. We designed that R is much larger than the reactance of your capacitor. This one is XC, reactance of your capacitor. Okay, if this is this R is larger than XC, so Vs equals to 1J omega C divided by R. Okay, this part can be ignored. Next thing, the negative Vs times negative J1 omega C R. This is your VC. Do you understand how to do this step?
Why are you not?
Oh, why we ignore this part?
Yeah.
We design R is very large, much larger than XC.
Okay, the whole XC.
Yeah.
Okay.
Yeah, whole XC. Okay, we get this one. There's a J here. So what's your Vs? Your Vs is J omega lambda. Then times negative J1 omega C R. So J times J is a negative 1. So negative is cancelled. And omega is cancelled. So it's 1 CR times lambda. So your C is constant, R is constant, and there's no phase shift. So your VC and lambda are in phase. They have the same angle. So we can use VC to represent lambda. And your lambda can replace B. So that's why we can use this VC to replace the B. Okay, so in this model I posted on Canvas. So when you design your circuit, you need to add the capacitor here. You need to add the capacitor in series with your R, your resistance. But what's the value you choose for your capacitor is up to you. Okay? So yeah, let me see. We still have 5 minutes. We can see the correct answer. This is the correct answer. So this is your pH curve. Put your primary side current as your X and the capacitor voltage as your Y. Then you can plot the pH curve. Here, you can see the flux. Oh, in P-scale model, you can measure the flux directly. Okay, but we don't use that for this problem. You need to use voltage and current to plot the pH curve. Don't use flux. I just want to see your flux. You can see they are in phase with the flux is in phase with your capacitor voltage. See, in phase. But your Vs, this voltage has a phase difference with flux and VC. Right? It's a 90-degree difference. So that's why we cannot use this voltage. And for your primary side, secondary side, and magnetizing current. So you can see your IS is almost 0. We can ignore that. And your IP equals to your IM. The magnitude equals to IM. But it has a 180 phase shift. That's because here, oh, you guys cannot see. It's here. In your P-SCAD module, the IM is mirrored. The default direction of the IM is out from positive polarity of primary side. What's that mean? can see this figure. You measure the current like this way, but this transformer measures the IN this way. This way is the positive. This way is the positive direction. So that's why you have 180 phase difference. Okay. Did it make sense? Okay, the last thing, if your design is incorrect, if your direction is incorrect, you will get this pH curve. It's not correct. That's because you add a large resistor, but there's no capacitor. So when you download the PSCAD model post on Canvas, you will get, when you run it directly, you will get this curve. Because we didn't add the capacitor there. So it's like this. You use this Vs as your phi, so you got this wrong value. And one more thing, one more page. If you add the resistor and the capacitor, but when your resistor is too small, you will get wrong pH curve again. Okay, because you see you have IS. If you have IS, you cannot use the IP to replace your H. This equation. If your IS is not 0, you cannot use IP to replace H. Yeah.
What is IM?
IM is a magnetizing current.
So that's like the little inductor in the middle?
Okay. Do I have the circuit? Oh yeah, I have here. If you have, in the real life, you have the core part, you have middle part, right? You have this part in your
I was talking
transformer.
about that.
Yeah, IM is this one.